Hi guys, today I will be explaining the gap filling method of random forests, how they are useful for filling in gaps, how they are related to decision trees and how they are made up by decision trees, also why they are a good method of gap filling. So to start off, we're going to talk about decision trees just because a random forest isn't a forest without the trees, since the random forest is made up of a bunch of trees. So basically what a decision tree is, it's a tool used to help decide on possible outcomes or possible consequences by analyzing certain attributes. In the case of the decision tree on the right, it's just trying to determine whether you're going to go outside to play baseball or not based on the weather. The attributes that you're analyzing are whether it's sunny, overcast, and rainy, and that's how you'll determine whether you'll play or not. If it's sunny in this case, two out of the 5 times you'll go play, and then the reason being is because after that you're gonna look at another attribute, whether or how to see how humid it is. If it's under the 70 degrees humid, then you're gonna play. If it's over 70 degrees, then you're not gonna play. In the case of overcast, if it's overcast, you're gonna play. When it's rainy, you're gonna have to look at another attribute, whether it's windy or not. If it's windy, then you're not gonna play. If it's not windy, then you do play. So that's basically what a decision tree is. You look at the different outcomes and it gives you the best decision as to what to do. A decision tree, though, is considered a weak learner because it only has a small portion of the entire data that you're analyzing. So it's a weak learner in the sense that you don't have all the data, so you can't get a good decision. The tree acquires its data by bootstrapping. What that means is that you get data from an entire data set with replacement. I'll go more into the bootstrapping on the next slide. So bootstrapping, as I said before, is when you randomly pick data from a data set with replacements. So you do this in order to have unique data on every tree. Also, what this does is eliminate bias in choosing data, and it presents variance in the trees because they will all have different data. Because you're replacing the data back into the data set, you actually don't end up using all the data in your data set. Most of the time, you actually end up only using 2/3 of it. That's what gives it this variance, because you don't know exactly how much data you're going to use, you don't know exactly what data you're going to use, and that's what presents the variance, so as to get a better decision at the end once you put each decision tree together to make the random forest. Back to weak learner versus a strong learner. As I said before, a decision tree itself, a standalone decision tree, is a weak learner because it only has a small portion of the entire data. The strong learner is the random forest, because what you're doing is putting a bunch of weak learners together, which is a bunch of decision trees together, to make a strong learner. With a lot of different outcomes, you're going to have a better decision as to what or what not to do. And that's the reason that we use that's one of the many reasons that we use the random forest, in order to get a better outcome of your data. So what exactly are random forests? A random forest, simply how I've said in the past few slides, is a collection of decision trees. You use them pretty much to obtain a better result for the set of data that you're analyzing. You just want a better decision in the final outcome of that data that you're analyzing. So why use a random forest and not just a simple decision tree? So when you use a single decision tree, you have a high variance in your data, mostly because you're not looking at the entire data. There could be data missing, you could have an outlier, many different things as to why there's going to be a lot of variance in there. You use multiple trees in order to get a more accurate outcome. And then accuracy and variable importance are generated automatically. So you get the variable importance and accuracy just because you have many different decisions, many different data points that are randomly selected. So you're giving importance to each data point because they're chosen at random. Also, with random forests, overfitting becomes less of a problem than with simple decision trees. And random forests are not very sensitive to outliers in training data. So the outliers won't skew your data towards them and make your data bad for it. It also has an effective method for estimating missing data and maintains accuracy when a large proportion of the data are missing. So this goes back to the actual gap filling. So when you're actually trying to estimate the missing data, the way that random forest works, because you're getting a lot of the data around it and just a lot of the data from the data set, you get a good outcome as to what the missing data will be. You're not just gonna guess on what your missing data is going to be just by glancing at it, by putting a bunch of decision trees together, making the random forest. You're gonna get a better estimation of what the missing data actually is. So what a random forest does is so after building a forest by bootstrapping all the decision trees, you take the sum of all the trees and you divide that by the total amount of trees that there is in order to get the better decision. There's the equation right there to the right. So the P is a probability for C, which is the many outcomes that each has. So depending on your decision tree, there could be different outcomes. On the first one, it was a yes or no. Nick from our group worked on an example. His trees right here. It's also a simple yes and no. So in that case, your C would equal 2. It's just the different outcomes that there is depending on what kind of decision tree you're looking at. That can go up to 4. It can go up to a lot more than that. In this case, this is one tree of given all the decisions, whether it's yes or no. So in what you do is you would make a bunch of those trees, and you would take all of the decisions, you'd add them all up, and then you'd essentially divide by how many trees there actually is. Since each tree does have a different outcome, you're pretty much, like I said, you're pretty much taking the outcome of each tree and averaging them out to get the best possible outcome